Hello and good morning, good afternoon, or good evening, wherever you may be around the world today. My name is Chris Ball, and I'm with Vector Corrosion Technologies, and I'm your moderator and host for today's webinar series. This webinar is presented on the behalf of the Concrete Preservation Alliance, and this is our 5th year of presenting online webinars to deal with concrete investigation, preservation, and corrosion mitigation. We are on our 39th webinar, which is amazing to think how far we've come through the years. This is the first of a 4-part series on advanced assessments, and happy to welcome you guys from wherever you are. Today's presentation is entitled Hidden Threats, Advancing Techniques for Investigating Corrosion in Post-Tension Structures. As I mentioned, this is presented on behalf of the Concrete Preservation Alliance. The purpose of the Concrete Preservation Alliance is effectively to promote sustainability, good concrete repair practices, and new and innovative technologies into the market. The home base for the CPA is the website WeSaveStructures.info, which you guys use to register for today's webinar. The Concrete Preservation Alliance includes a number of members. As I mentioned, Vector Corrosion Technologies, Vector Construction, NDT Division, BCS Engineering, and Structural. On the We Save Structures website, where you registered for today's webinar, you'll find a host of information regarding not only webinars, but also a seminar series which is ongoing, which I thought I would just take a second to mention. It's the We Save Structures Seminar Tour. Next week, it's not too late to register. This is an in-person webinar or a seminar series that is basically entitled Using ACI 562 Repair Code and ACI 563 Repair Specifications to achieve durable concrete repairs. These are half-day in-person seminars. And next week, the 3 final locations for 2025 are April 29th in Springfield, Illinois, April 30th, Kansas City, and May 1st in Minneapolis. Also on the Concrete Preservation website, WeSaveStructures.info, you'll find a handy environmental impact calculator. So we know that one of the most sustainable things we can do in construction is to keep our built environment in place. And to aid in that endeavor, we have a open source free impact calculator for the preservation of concrete. So you can use this information. You basically will put the number of cubic meters or cubic yards of concrete that you're keeping in place through repair, rehabilitation, and service life extension. And it'll give you all of the pertinent information with regard to the avoidance of carbon production, saving potable water, and how many tons of rubble that you will keep out of our landfills. So please feel free to visit the WeSaveStructures.info site for that information. And to encourage audience participation and questions, we do offer a $100 Amazon gift card. In order to qualify, we don't know who wins unless you identify yourself. So anonymous questions, we may be able to answer those in the live chat at the end, but we won't be able to identify you to award your gift card. So please use your name. You can ask as many questions as you want, And our co-presenters today will pick the winner with the best question. And with regard to our co-presenters, we're pleased to have two highly experienced, qualified engineers with VCS Engineering. Natalia Shanahan has a PhD and is also a professional engineer. She went to the University of South Florida in Tampa and is well known for her experience in investigations, concrete materials, and as well as durability and service life modeling. Our other presenter today is Pratik Mukut. He is also has a PhD from Oregon State University, is also a professional engineer and a NACE cathodic protection specialist. And he will be presenting today with regard to many of the non-destructive testing techniques that are used for post-tension structures. So with that, I'll turn it over to Pratik to begin today's webinar. Thank you.
Thank you so much, Chris, for the introduction. Perfect. Thank you, everyone, for joining in today and taking your time to attend this today's webinar on corrosion mitigation and investigation of bonded post-tensioning structures. In terms of the outline, I'll be going over a brief background of the PT structures in US and globally. What are the primary concerns they face? What are the typical investigation tools we use to investigate or to probe the corrosion susceptibility of those structures? We will go over a couple of case studies and then into rehab options or corrosion mitigation options. So to dive into a brief background about post-tensioning structure, the concept of post-tensioning was first introduced in 1928 by a French structural engineer, Eugene Freyssinet. And as a consequence of developing those ideas, the first post-tensioning bridge was constructed in France in 1941. And especially during World War II, where there was a significant steel shortage, the post-tensioning structures gained popularity owing to the steel shortage and also post-tensioning structures making the use of rebar less prevalent. In United States, the first PT bridge was constructed during 1949 to 51, and that's the Walnut Lane Bridge in Philadelphia area. And as we all know that these PT structures or post-tensioning structures are structurally efficient and we can build really long spans out of them. In terms of history, I'd just like to briefly go over the major failures that have happened in the history of US bridges. And if you note all of these failures, most of them or almost all of them can be attributed to either improper grouting or ingress of chloride contaminated or contaminated deck runoffs. So essentially, when it comes to durability of post-tensioning structure, what matters is the homogeneity of the grout that's in the vicinity of the tendons and the voids or like how good they were poured in. So speaking of causes that cause PT corrosion, there are two main culprits. One is improper grouting operations or improper grout material. It can lead from water bleeding or excessive water in the grout mix, or it can also come from segregation of the grout material. Sometimes inadvertently or accidentally, chlorides might be added to the grout in the form of admixtures. So that can result in higher chloride levels, exposing the strands to higher chloride levels, which results in corrosion. And then on the other side, we have moisture, external contaminants, which can be introduced into the duct through end caps or through cracks in the duct. And that can result in environment that are very conducive to the corrosion of the post-tensioning strand. And I'll go over these concerns or these causes in the subsequent slides. Here are some of the pictures which highlight typical failures. The one on top is a bridge in Pennsylvania. Here you can see the reinforcement, regular conventional steel reinforcement. You also see a post-tensioning duct here, which is completely eaten out by or completely corroded, and now you have the strands that are exposed to chloride contaminated runoffs from the deck. So essentially, the rebar corroded first. It led to cracking and effectively spalling of the concrete, which led to a direct path uh, of chlorides to the metal duct, which resulted in severe corrosion and heavy section loss of the duct. Effectively, that resulted in the exposure of the tendons. In the bottom images, you can see the external post-tensioning system where you have obvious grouting defects or voids in the duct that has led to exposure of tendons to the elements like moisture or chloride environments or a lot of oxygen, which has resulted in the corrosion of the tendons. In some cases, the damage was so severe that it had resulted in the tendons being completely severed and resulting in a complete failure of the tendon. So when it comes to failures and when it comes to segregation of grout or grouting defects, the profile of the tendon matters a lot. If we are talking about a straight profile, there are high chances then when the grouting operations are being conducted that the tendon will be uniformly coated with the grout material, which is of high pH, highly alkaline in nature, and that high pH or passivity can protect the steel from future corrosion. Whereas if you have a deviated tendon or an incline or a vertical tendon, you tend to see the grouting defects being more prevalent, especially because some sections of the tendon could be completely exposed, whereas the others are completely grouted. In the completely exposed sections of the tendons, you have no protective layer or no oxide layer that's being formed because of the high passive, highly alkaline grout, and that's why you have higher susceptibility of corrosion and eventual failure in those uncoated sections or unbonded tendons. Sometimes, or in some cases, when you have high amounts of water in the grout, that can result in segregation, whereas where the cement particles or the heavier cement particles tend to settle down and they tend to cure or consolidate first, that results in bleed water on top layers. As you keep consolidating or curing the grout, it keeps on pushing the bleed water up and you have increasing water to cement ratio. And as a consequence, you tend to see higher levels of contaminants or like deleterious species like chlorides or sulfates being towards the top because of excessive amount of water or higher water to cement ratios. What it results in is you have incompatible material in the same duct. Even if the duct is completely full of grout, you can have segregation and that will result in an incompatible mix where you have top tendons being exposed to a very powdery grout or or a grout of higher water to cement ratio. It can be clay-like, or when the water has completely dried out, it can be powdery material, and that provide essentially no strength or no bonding. Whereas at the bottom, you have really good bonding to the grout. This in chemical incompatibility and the strength incompatibility can result in corrosion, where the top tendons can experience significant corrosion because of lower pH or lower alkaline environment, whereas the bottoms are completely immune of corrosion, especially because of high pH grout surrounding them. So segregation and voiding defects are two key concerns when it comes to bonded post-tensioning structures. Now we know what the key concerns are and what are the species that might lead to corrosion of the post-tensioning strands or post-tensioning tendons. What do? We have some investigation tools at our disposal which we can use to probe the PT structures and to see what are the potential areas of defect or where the areas of issues are. In today's presentation, I'll go over a couple of techniques which will talk about how we investigate the structure, how we probe the post-tensioning strands, visual confirmations. I'll go over ground penetrating radar, impact echo pulse velocity, which is essentially acoustic technique, borescope imaging. This gives us a visual confirmation of our GPR and impact echo techniques. Then we have moisture testing, which gives us the probability or the risk of corrosion the strands are at. And eventually we'll go into the material testing. So to begin with, for all the internal bonded post-tensioning system, any investigation starts by locating the tendon, and we use ground penetrating radar to locate the tendon or the metal ducts, where it's a fairly straightforward technique where you send an electromagnetic wave into the concrete and you wait for the reflections to come back. And on this chart or on this graphic you see here, each peak or each parabola you see here is a presence of a steel object. That steel object can be a reinforcing steel or it can be a post-tensioning duct. To an experienced eye, it's easy to discern between the reinforcing steel and the post-tensioning ducts just by looking at the contrast signatures or the peak signatures. And once you do the GPR scans, you just lay out the drape of the tendon to track the profile of the tendon. And we mark, sorry, we mark that profile every 1 feet for subsequent testing using maybe sonic or some other testing. So once you lay out the profile of the tendon, you often use sonic or ultrasonic. We call it impact echo or pulse velocity technique. Essentially, this technique relies on sending a sound wave or a sound signal, or you can call it mechanical wave or a stress wave, into the concrete and wait for the reflections to come back from the back surface and also from the duct surface. Essentially, you place the sensor and you make an impact using a pneumatic impactor. You send the sound waves in. If the duct is completely full of grout, then you will have a quicker reflection. Whereas if you have air void or if you have any voids present in the duct, then it might take a lot longer for the sound wave to come back to the sensors. And this essentially is analyzed in the frequency domain. Our device can do impact echo and pulse velocity both at the same time, but when it comes to applications for post-tensioning applications, we more often rely on impact echo than anything. In terms of instrumentation, as I had mentioned, we use a pneumatic impactor. We use steel ball bearings to make the impact on the concrete surface above the tendon. And then we have a sensor array which has 4 sensors which are waiting for the reflections to come back, and that will give us the data. Here is one of the videos from one of the projects we were working on, where you see a technician holding a sensor array, all the 4 sensors he is holding, and he will place on the concrete surface. This testing happens when you have already laid out the post-tensioning strand or like the profile of the post-tensioning duct on the concrete surface, and then you just follow the profile, you make the impact and you do the testing, and it goes something like this. So you make an impact, you place the sensor, make an impact, place the sensor, make an impact, and it collects the data while you're doing so. And you can see the pace of the testing, it goes pretty fast. So you lay out the tendon, you do the impact echo testing, and this is the system what we use for internal tendons. We can use a similar system for external tendons where you have a transmitter and a receiver on the opposite ends of the external post-tensioning duct, and you send a signal from the transmitter and you receive that sound signal from the receiver. You have an idea of the exact diameter of the duct, and that helps us know if the defects are present and to what extent the defects are present. Usually we do this testing at 10 o'clock, 2 o'clock, 4 and 8 o'clock positions. And that way we perform a comprehensive testing to see if the defects are present and to what extent. Once you have identified the extent or the location or the areas of potential defects, then we need to visually confirm if the defect is actually present or if it was a false positive. And one way to visually confirm the results of impact echo testing is using a borescope. In this, we make an opening in the concrete, we open up the metal duct and we put a pinhole camera into the metal duct to see if the voids exist or not. In most cases, if a void exists, you will be able to put the camera through the duct and see what's happening inside. One of the images shown here, it shows that the tendons are completely coated with the grout, but you see that uh, the rest of the duct, it's completely empty. You do not have any grout whatsoever, so there is a large void there. In the second image, you see surface corrosion of the post-tensioning strands. This video is from one of the projects we were recently working on. And you can see in the video that the top half of the duct, there is no grout whatsoever, whereas on the bottom half, you see some history of grout there, and you can see severe or heavy surface corrosion of the strands. In this case, since you do not have any high pH environment that's usually provided by the grout, you do not have any passivity or you do not have any form of protection. So if moisture was to come in or if chloride contaminated water was to seep in, it will get directly in contact with the strands and it will start surface corrosion. Same project, another video that shows significant section loss and and pitting on the strands, and you can see like these strands are heavily corroded. Just the fact that you are able to put the boroscope in should raise a lot of flags, because if you're able to put a boroscope in, obviously there is a void present. If a void is present, the second next question is, are the strands corroded because of the contaminants or the moisture that may or may not have gotten in? This slide typically shows typical defects we encounter. I would like to draw your attention to the image on the bottom right, where you see some reflection of the boroscope light, and this is essentially freestanding water at the bottom of the tendon. Obviously, you have a large void. The strands are completely exposed and you have no protection of any sorts. And then on top of it, you have freestanding water. It's an ideal scenario where the corrosion would most likely happen. And you can see some patchy corrosion already happening there. So this is an alarming sign that the failure is ought to happen in future. Another example is you have a duct corrosion. It's completely voided, no signs of grout. And you have a Dewey-Deck bar that has a severe surface corrosion. You have severe section loss in some other cases, but in all the cases, you can see that the boroscope was able to go into the duct, and that's a sign saying that, okay, there is a void present, you need to do something about it. If there is any freestanding water or if the relative humidity of the duct inside the duct is pretty high, there is high chances that the exposed tendons will corrode. And with increasing relative humidity or moisture, the corrosion rate goes up. The higher the corrosion rate, the more will be the section loss and the quicker will be the section loss. And if you have section loss, obviously those strands will fail due to being under immense amount of stress. To measure the amount of relative humidity or to measure the relative humidity inside the duct, we use something called as moisture testing, where you drill into the concrete, you drill into the duct and you make maybe a ½ inch or a ¼ inch opening, and you have an input, you have a similar output, you have a flow meter, and you try to push a dry gas through the duct. Essentially, we are trying to measure what's the relative humidity inside the duct using a dry gas. Dry gas will absorb all the moisture it can, and we measure the moisture content on the output, and we see what's the relative humidity inside the duct. Based on the relative humidity, you can classify the tendon as dry, moist, which is wet dry, and then wet cables. If the relative humidity inside the duct is pretty low, you will land up in a dry zone, which means the tendons are less susceptible to moisture-induced corrosion or corrosion that may happen because of moisture and oxygen. Whereas if you have a relatively higher humidity, then your tendons might end up in a moist zone or a dry wet zone. You have slightly higher chances of moisture-induced corrosion. Whereas if the relative humidity is high, you will land up in a wet zone where you have almost like extremely high chance of corrosion being initiated because of moisture. And beyond moisture, there are other factors that will end up affecting the corrosion. It can be availability of oxygen, it can be presence of grouting, and so on and so forth. But knowing the moisture content can give you a lot of insights into how much corrosion we can expect on the tendons. And then in addition to all these tests, we often do material testing, which includes measuring the pH of the grout, measuring the chloride content of the grout, and doing petrographic analysis on the grout material. And I'll let my co-presenter Natalia talk about it some more.
Thank you, Pratik. The materials testing that is typically conducted on grout samples is pH testing, chloride concentration testing, and less frequently petrographic analysis. pH testing is typically done at large openings where a section of the duct is removed to expose the grout. You can use a rainbow indicator solution, which changes color depending on the pH range, or you can use a phenolphthalein indicator, which is what you see in this photo. The phenolphthalein indicator changes color to pink when the pH of the grout is above 9.5, and if it's below 9.5, it remains colorless. If there is a suspicion that there is environmental exposure to chlorides that is leading to chloride contamination of the grout, it is a good idea to test the chloride concentration of the concrete surrounding the duct, in addition to testing the grout. So in this example, we collected 3 grout samples from different tendons. Sample 1 was collected at a high point, samples 2 and 3 were collected at low points of the drape. There was some leaking from the deck, and there was a concern that chloride contamination was coming from exterior exposure to chlorides. So we collected concrete samples near the grout sample number 3, which you see in the table below. And there is environmental exposure to chloride. There is environmental exposure to chlorides there. However, the chlorides in the concrete are not nearly high enough to explain the high concentration of chlorides in the grout. So most likely what happened on that project is that the grout was contaminated during construction. Most likely when the ducts were flushed with chloride contaminated water prior to grouting, and that water was not properly dried out and remained at the low points of the drape. Typical thin sections from petrographic analysis are shown on the left side of the slide. Here we have 2 different samples that were collected from the same project. Petrographic analysis is typically used to verify that the grout is cementitious. It can also determine the presence of supplementary cementitious materials and also give us a comparison of the water to cement ratio in different samples. As you can see, sample number 1 has a much more intense blue color. The blue here is coming from the epoxy that is used to stabilize the grout samples for a thin section. And the prevalence of the blue in sample 1 indicates that it has a higher water to cement ratio because more epoxy was able to penetrate into the capillary pores in the grout. So the higher the capillary porosity, the higher the water to cement ratio. The images below show an example of pore infilling for sample 1. So in sample 2, pores are blue, which means they were empty and the epoxy was able to fill them. But for sample 1, the pores were filled with secondary ettringite, which indicates exposure to external moisture. So we're going to present 3 different case studies today that illustrate the use of different techniques that Pratik had discussed. Our first case study will be on testing of post-tension bridge piers. This bridge is located in Virginia and uses U-shaped post-tensioning tendons in all the piers. So all the piers have these A tendons that are colored in red circles on the cross sections that you see on the left side of the screen. The Riverside piers, which is the cross section below, has an additional pair of U-shaped tendons. They're colored in blue circles that are referred to as B tendons. Next, please. Our testing focused on the 25 feet of the tendons at the top and bottom of the piers. And for B tendons in the river piers, because they extended into the girder, we were also able to test them inside the girder. We performed impact echo testing that was followed up by borescope inspection. As Pratik mentioned, impact echo testing can't differentiate between different types of defects. So grouting defects can be benign. Those are lens voids or rind voids that do not expose the strands to the air. So the strands are fully coated. However, there is a void between the grout and the duct, and this will be picked up by impact echo testing as a potential grouting defect. While other defects, such as voids that do expose the strands and soft grout, create a corrosive environment for the strands. So based on the results of impact echo testing, we selected locations for borescope inspection, and this is what helps us to differentiate between different types of grouting defects that are identified by impact echo. Based on impact echo testing results, majority of the borescope openings are located at defect locations, and we do some openings in fully grouted ducts as well for verification. So when the results are combined at the end of the project, we produce drawings that you see on the right side of the slide, where the tested tendon sections are color-coded based on impact echo and borescope results. The tendons that are colored in green indicate that impact echo testing showed that they were fully grouted, and this was confirmed with a borescope. Yellow color indicates also fully grouted tendons according to impact echo, but they were not confirmed by borescope inspection. Red color indicates a void that was confirmed by borescope inspection, and orange is a void in impact echo, but not confirmed with a borescope. In addition, when we make a borescope opening and there is grout present, the technician probes the grout with a screwdriver to determine if the grout in the duct is a hard, high-quality grout, or if it's a soft grout that creates a corrosive environment for the tendon. At the bottom of the slide, you're seeing some borescope images. So although we did find voids on this particular bridge, minimal corrosion was observed on the strands. One interesting concerning thing, the only concerning thing that we found was a broken wire that you see in the borescope image on the left. Next. Okay, our second case study is going to look at testing of external post-tensioning. This is Ringling Bridge in Florida that uses external post-tensioning inside the girders. The investigation for this bridge was initiated by a tendon failure. So the photo on the right shows on the left shows the impact echo testing of external tendons. And the image in the middle of the slide shows the impact echo and pulse velocity data that was collected on a fully grouted tendon. So although our device collects the impact echo and pulse velocity data at the same time, For locating of grouting defects, we don't really use the pulse velocity data because it's looking at the velocity domain. We look at the impact echo data. The principle here is that the frequency of with which the wave resonates in a concrete section is related to the thickness of the section. When we have an internal or an external tendon that is fully grouted, we will be measuring the frequency that corresponds to the true thickness of that element. So whether it's the true diameter of an external duct or the true thickness of the web or the deck for an internal tendon. So as you can see in the middle image, the impact echo data shows a very consistent frequency for all the measurements. Now, if we look at the image on the right, it's a very different picture. Here, the data was collected on a tendon with grouting defects. So this tendon was confirmed to have voids. If we look at the impact echo data column, the frequency is all over the place. There's a significant change in the signal shape as well that indicates the scattering of the wave by the presence of the voids. And actually, if we look at the pulse velocity data as well, there's a significant change in the signal shape as well. Next, please. So here the owner decided to remove some of the voided ducts, and these images show some of the duct sections that were removed from the bridge. Here we see a void at the top of the duct in both of these sections and corrosion on the surface of the exposed strands. In the third case study, we're going to take a look at evaluation of post-tension pier caps. So impact echo testing can only be applied when the thickness of the element is 2 feet or less. At greater thicknesses, we're not able to locate grouting defects with our device. So as you can see, these pier caps were significantly wider than 2 feet. So we couldn't use the impact echo testing approach. So instead, because the anchorages on these pier caps were easily accessible, we removed the pour backs and did visual inspections of the anchorages. And as you can see on the slide on the bottom, we found some missing grout caps. And on the top, the image shows that there was voids in the grout caps at some locations. And where there was missing grout, there was heavy corrosion on of the anchor plates, as well as strand tails. So in addition to the visual inspection, we did borescope inspection of the grout ports, moisture testing of the tendons, and we also sampled the grout for chlorides. This slide shows an image of the borescope inspection where the technician is feeding the borescope through the grout port. This was done on the grout ports that were empty. Obviously, we were not able to do it on grout ports that were full. And, you know, good news, majority of the grout ports on this project were in fact full. In the grout ports that were voided, 6% had lens voids that are benign and don't put the strands at risk for corrosion, and 13% were fully voided. And at the bottom of the slide, you see some typical images from the voided grout ports. We also performed moisture testing. So here we pushed the dry air from one end of the tendon to the other. As you can see on this chart, majority of the tendons were in the dry wet or wet condition, which puts them at risk for corrosion. The chloride samples of the grout showed that majority of the samples had chloride concentrations below the corrosion initiation threshold, and only one sample had a high chloride concentration. And this was because the pour back actually didn't cover the grout port at that location. It was left exposed, and chloride contaminated water from the deck ended up getting in there. So once we locate the different grouting defects, what can we do to mitigate corrosion of the strands? We have three different options. We can perform drying, anti-corrosion impregnation, or regrouting. If there is moisture present in the tendon, if there's bulk water or high moisture, the tendon can be dried out. The PT drying process is very similar to the moisture testing process that Pratika described. There is a supply of dry gas that's connected to an import. This is typically placed at the bottom of the tendon drape, if possible. It's not always possible depending on the setup. And then there can be one or two outports that are connected to a flow meter that is also connected to a moisture meter that is recording the relative humidity and the temperature coming out. The dry gas that is supplied through the import pushes the air inside the tendon through the outports, and this process continues until the air inside the duct is dried out to below that threshold line that separates the dry tendons from the moist tendons. This is an example from an actual PT drying project in Florida. So this was done on a bridge that had bonded PT in the I-beam girders. What you're seeing on the left side of the screen is the dry air plant that was set up at one of the abutments and supplied dry air into the girders. And on the right side is a photo of the two outports that are connected through tubing to a moisture meter. Next. On this project, we used a remote monitoring system, so that tubing was connected to this system that is being set up in this photo. And the black case had a data logger that sent all the data to a website, so it could be monitored remotely. This plot shows the relative humidity and the temperature of the tendons at the very beginning of the drying. Again, as you can see, everything is above the green threshold line, so it's a high risk for corrosion. There is one tendon that is actually at 100% relative humidity, and when we drilled that one, water came out of it. And then the plot on the right shows the relative humidity of the tendons at the end of the drying process. So all the tendons except for one were below the green threshold line, so they're in the dry condition. At this point, the drying for these tendons was terminated, and there was one that was still remaining in the moist condition, so drying for this tendon continued. The next one is PTI, or anti-corrosion impregnation. So this can be done when there is voids in the duct. If there's moisture, it's recommended to, especially if there's significant moisture, it is recommended to dry the tendon first before doing the impregnation. Also, impregnation is very effective in addressing areas of soft grout. During the impregnation process, a low viscosity silicon-based polymer resin is injected into the tendon. It can be injected through the anchorages or at any point along the tendon length. This material has an extremely low viscosity. It travels inside the interstitial spaces around the king wire and coats the exposed strands in an anti-corrosion coating. This material will also penetrate into the voids surrounding the strands and areas of soft grout. This slide shows injection of the anti-corrosion material through the anchorages. You have a schematic on the left, and the the photo on the top of the right side of the slide shows the caps with ports installed and the tubing, which is used to push the impregnation material into the anchorages. The photo of the anchorage on the bottom actually shows you the anchorage on the opposite side of the tendon, opposite from the injection side. So you can see the darker color for 2 of the strands there. This is where the impregnation material is starting to come out. So when the impregnation process is completed, all the strands should have that dark color. Next. Okay, this slide shows impregnation for an internal tendon at a point that is away from the anchorage. And then the photo actually shows impregnation of an external tendon. So for external tendons, there is a saddle that is attached at the impregnation point. An opening is made through the saddle. Next, please. And then a port supplying the impregnation material is connected through the saddle and the impregnation begins. Next, after the saddle is removed, the impregnation can be confirmed. Here you see the darker color of the grout. This is the penetration of the impregnation material. And also in impregnated areas, the strands have a higher sheen to them, which confirms the presence of impregnation material. Next, please. Okay. Here is a verification of PTI impregnation. Again, you have the darker cap on the left, the darker anchorage on the left, that's coated in the impregnation material, and on the right for comparison is the anchorage that has not been treated yet. Here's another verification opening. Again, you see the darker color of the grout, which confirms that the anti-corrosion material got to that point. And here's an up-close view that shows the higher sheen of the strands from the coating. And this video shows an impregnation material. That's what you see bubbling through. So that's the impregnation material being pushed to this opening. Next. And our last technique is regrouting. When there is large voids present along the tendon, the tendons can be regrouted. Grouting can be done using the positive pressure approach. This is what you see on the slide, where grout is pushed in from the low point and the technician watches for the grout to come out at the high point of the tendon drape. Grouting can also be done using a vacuum assisted grouting. Now, the important thing to remember is that tendon regrouting needs to be done with a material that is electrochemically compatible with the original grout. So if the cementitious grout was used during the bridge construction, a cementitious material needs to be used for regrouting as well. Otherwise, if the materials are dissimilar, it can create a corrosion cell. So in summary, PT tendons are susceptible to corrosion in areas of grouting defects, but there are evaluation techniques that are available to determine the cause, extent, and location of the problems. And there is also corrosion mitigation strategies that exist to protect and extend the service life of PT tendons in existing structures.
Okay, all right. Well, thank you, Pratik and Natalia, for all the excellent information, and look forward to going through some of the questions. We have quite a few questions, and obviously we're not going to be able to answer all of those or ask or answer. However, we will be sending all the questions to the presenters, and they can follow up with you directly if we're unable to get to some of your questions here. So, Pratik, I was just going to start off with you. We've had a number of questions around this area. I'll just kind of summarize, and I guess it's kind of part A and part B. How do you know if a structure needs to be tested? You know, are there telltale signs where you want to do like a more in-depth inspection like this? And if you're going down that path, are you looking at the whole length of the tendon or all of the tendons? Or are you doing areas where you know that grouts or voids are typical, or any comments upon the selection of the sample areas?
Right. So everything begins by visual inspections. If a structural engineer is making the assessment that the structure is cracking and those cracking can be attributed to post-tensioning in the structure, then obviously that prompts the investigation, and we need to investigate if there are any failures, tendon failures in the PT system. So essentially the answer is a telltale sign would be a cracking or large spalls on the structure that can be attributed to the post-tensioning structure. That's one. And second thing is the owner's approach can be proactive or reactive based on the budgeting. If the proactive testing reveals that there are some voids in the PT system or in the ducts, then that's the best time to act on it, because the corrosion has not advanced to the point that it has caused any serious failures in the post-tensioning, which might eventually lead into more cracking. So I would say proactively testing the structure would be really worthwhile owner's money, but in most cases we have seen that cracking in the structure has prompted the investigation of PT systems. In terms of the extent of testing, again, in most cases, doing a sample area, like let's say like 5, 10, or 15% of the representative areas, focusing on the worst areas, which shows the majority of the cracking, and doing a non-destructive testing like impact echo would give us idea as to if there are any grouting defects. And then if the impact echo testing concludes that, okay, there are any potential defects, then we might go deeper into it, open up the duct and do a borescope investigation or do some material sampling. But I would say 10 to 15% representative area is a good starting point for proactive testing.
Okay.
Natalia, you would like to add anything?
Yes, thank you. I'd like to add to that. We all know that structures up north suffer from de-icing soil deterioration in the decks. So if the owner is planning a significant investment in the structure to rehabilitate the deck and any other areas that are affected by chloride-induced corrosion of the conventionally reinforced elements, it would be a good idea to at least do some testing to verify that there are no issues with the PT, which is typically in the girder webs, because the testing would be rather small compared to the budget of the rehabilitation, and it would be worthwhile to confirm that there's no additional interventions needed or that there's no additional concerns with the PT that might change the rehabilitation approach.
Right.
Okay. Thank you, guys. Natalia, while I still have you here, I'll pair a couple of questions together for you, and these are more around standards. There's a few questions related to chloride testing, and I guess a general question is, you know, how many samples would you take? And then any comments about the differences in limits for acid and water-soluble chlorides? And then this part 2 is a question around standards related to the test method for humidity inside PT tendons.
So for chloride testing, it depends how comfortable the owner is with destructive testing. A lot of the times, what we see is that the owner wants to minimize the number of openings, and openings are necessary to collect chloride samples. Ideally, we would want to collect, I mean, it really depends on the linear feet of testing that we're doing, as well as the number of different exposures, the different exposure environments. For example, is the exposure to the bottom of the girder because there is leaks into the girder from the top of the deck? Is there something else going on? So we want to sample both areas that we think would be, so to speak, good areas as well as bad areas. In terms of chloride limits, because grout is going to have a significantly higher cement content than concrete, the corrosion initiation threshold for grout is also higher. So if we estimate a 0.5 water to cement ratio and approximately 1% air content, if my memory is not failing me, that threshold is around 800 ppm, where for concrete, we typically take 300, 350 ppm as the corrosion initiation threshold. ACI provides the threshold values for acid-soluble testing, and that's what we typically use. You can use water-soluble testing as well. However, in the grout, bound chlorides would be bound inside Friedel and Kuzel salts. So these are aluminate salts that contain chlorides. These salts are metastable, which means that if the pH changes, for example, if there's carbonation, or if there's a drop in pH due to initiation of corrosion, this would be a local drop in pH, local to the anode location. These salts would be destabilized and they will release the chlorides back into the pore solution. So we typically use acid-soluble chloride testing for grout.
Okay. Awesome, thank you. We've had a number of questions about new construction as well, and the concept of maybe using any of these techniques for quality control or testing, in a short period after the grouting process before the contractor leaves site to assure that the tendons have been properly grouted. Natalia, you want to take that?
Sure. Absolutely. These impact echo testing can be used as a QC test method, as well as borescope inspection of the grout ports, and that's completely non-destructive. But I have to say that grouting procedures have gotten significantly better over the years. There was a change in the PTI standards for grouting around 2012 that has solved a lot of these grouting issues that we're running into with older structures. So the structures that we're testing, they've typically been in service for decades. They're not new construction, but yes, these test methods can absolutely be used on new construction as well.
And I would like to add to this as well that a lot of owners have moved from conventional cement water grout to more thixiotropic grout, where they have like a non-Newtonian behavior. When agitated, they tend to flow really well, and when in a stable condition, they tend to solidify, and that has reduced the susceptibility for bleeding and segregation. So with improvement in material, that's a significant, like, less burden on the quality control, but nonetheless, QC testing must be done.
Excellent. At the risk of taking a little extra time, I'll just critique maybe one last question. We've had a number of questions around unbonded PT that's come in on buildings parking slabs, etc. Maybe just a quick comment on corrosion testing on those types of structures, and these techniques or others that you might suggest.
Right. So for when it comes to unbonded post-tensioning structures like parking garages or condominiums, we often use ground penetrating radar to locate the tendons or the banded tendons. We often use moisture testing to check, like to open the sheathing and to pass the grout, and then we do a screwdriver test to see if there is any loss of tension in the tendons. Usually for unbonded post-tensioning structures, we don't really use impact echo. In some cases, we have used corrosion potential surveys to test the anchors, but often it's misinterpreted, and often the owners tend to say that, okay, can we use corrosion potential survey for the, let's say, for the entirety of the strand? Well, unfortunately not. You can only test the metal components that are exposed to concrete, not the ones that are sheathed or has a plastic sheath on it. So to answer this question, we can use corrosion potential survey, screwdriver penetration tests, moisture testing, and ground penetrating radar.
Okay, I would just add onto that, as far as corrosion protection for those structures, you can do an extended drying period if you have wet tendons, and also regreasing of the strands, and in the areas with uncoated or exposed steel, could look at having some type of galvanic protection added. So anyway, yeah, well, thank you guys very much. Great questions, and like I said, we will have to send the rest of the questions to the presenters here. Just for the attendees, like I mentioned, this is the first of a 4-part series for advanced assessment methods. Please go out to WeSaveStructures.info to the events page, and you can register for the next session, or you can scan the QR code that you see right there. The next session is going to be talking about corrosion basics and causes and assessment strategies for condition assessments on more conventionally reinforced concrete structures, and Pratik will be presenting on that webinar. And once again, if you have any questions that you think of after the conclusion of the webinar, there you see Natalia and Pratik's contact information, and they would be more than happy to follow up with those questions, or even if you'd like to have a presentation for a local office for your firm, or follow up on specific project inquiries, there's your A team right there. So with that, thank you guys for attending. We certainly appreciate your time, and we hope you enjoyed the presentations and maybe took away 1 or 2 things that you can follow up with. And until we see you again in May, let's go save some structures.
Thank you, everyone.
Thank you.